Welcome back, and our second presenter is Mike Roan from Penn State University. One of the things that we've all noticed with the advent and adaption of electric vehicles, is how quiet they are, and that's caused some problems. So they've started to add sound, which makes it sound a little weird. But Mike, you're going to explain why this is all for our benefit, right?
Yeah, I'm going to try my best.
Okay.
Yeah, so my name is Mike Roan. I'm from Penn State. This is some work. I've been at Penn State for about 2 months. Before that, I was at Virginia Tech for 16 years, and this is some work I did there with the Virginia Tech Transportation Institute. So Luke Neurauter, Marty Miller, and Michael Beard are all still down there at Virginia Tech, still working away on this stuff. So what's going on with all of this? You're starting to see more electric vehicles come out. Now there's like electric pickup trucks, the F-150 electric one's coming out, and soon pretty much all cars are going to be electric. Even tractor trailers are going electric. And one of the issues is they are very quiet, and so for the vision impaired pedestrian, they're a real challenge to detect them coming. And so people have been hit, and a lot of near misses. Here's an article that's from Australia that said a third of vision impaired people said they had a negative interaction, either hit or near miss, with an electric vehicle. So governments are putting out regulations that say you have to add sound to bring it up to where people can safely hear it, particularly the vision impaired. And I have a few of them there. The big one in America is comes out from NHTSA, the National Highway Transportation Safety Administration, and that's at FMVSS 141. And the EU has their own. There's a new one coming out in Australia, and they're all very similar. And really what they do, I don't want to get it, like, if we got into the details, it would take forever, but they prescribe how loud it has to be, and they prescribe certain conditions about what the frequency content needs to be. And then they also prescribe very rigidly how you measure your own vehicles to see that they're qualified. So there's like page after page of measurements set up. Government speak, if you read it, it's pretty crazy. You could go out and get it. And so what we did was we wanted to test, take a car, an electric vehicle, it was a Chevy Bolt, and put additive sounds on it. And we did 4 different sounds with different properties. And then we did the case with no sound, just the car by itself, no additive sound. And we had the car run by listeners who were sitting on the side of the road. One test we did, everybody was vision impaired. For this one, everybody wore those sleep masks that covered your eyes. And when they thought they heard the car, they pushed a button. And when they felt that the car had left the scene, they would let the button go. And so the big takeaways were here. So that was like 16 subjects did like 90 different cases of listening tests. And one of the big ones that we did this time around is to introduce something called probability of detection as opposed to just straight up average detection distance. And it provides a really cool picture of what's going on in terms of how these people detect the sounds. Although most of the sounds satisfied the regulations, people didn't always detect it. So even in our smaller study where there was fewer than 100 sort of scenarios, a couple % of the time, nobody heard the car. Which, even if it's 2%, when you extract it out to millions and millions of people interacting with these vehicles, that's going to be a good number of people who get injured. They do introduce, in Europe in particular, there's a big concern about noise pollution. I guess in America we don't care. Like, you ride your Harley down the street with it full throttle. But in Europe it's a big deal. Talk about the soundscape a lot, quality of life. And there is a good bit of extra noise pollution that gets put into the atmosphere when you take this approach. We discovered a little bit about our own testing, like how many times do they push the button when it's not there, false alarm rates. And the big one is you just can't beat physics. If you're going to use acoustics to alert people to something that's near them, acoustic waves propagate, and people further away are going to hear it, and you're going to have noise pollution. Just can't get around that. Some more details about the testing. On the top here is a picture from the sky down view. And there's 4 little blue dots in the middle, and that's where the subjects would sit, 4 at a time, and then the car would drive back and forth on the road. playing different sounds. To make it tougher, I mean, because if it was just really quiet, it's not too hard to detect the vehicle. To make it tougher, we surrounded them with some loudspeakers, and we blasted them with some noise at 55 and 60 dB, the noise. And it was kind of a special noise that was kind of the average background noise from an urban environment. So if we went out here in Seattle and stuck a microphone and averaged it over a week, we would get the spectrum of that, and that's what we reproduced. And so there's a nice picture of everyone sitting out there freezing on a December morning because we were out there all day, 8 hours. Every time an airplane flew by, we'd have to stop. So picture how excruciating that is when you see it appear on the horizon. You're like, no! And it like flies all the way across the horizon, and you have to wait for it to go by. Trains, dogs barking, crickets, birds, all of it. And then we put speakers on the front of the car. We know that's not realistic. They put the speakers up underneath. But this car was donated by General Motors. Doug Moore up there helped us out and let us use the car, but we can't go ripping it apart, so we put those on the front. And like I said, we did 4 sounds, 1 no sound condition, 2 speeds, 10 and 20 kilometers an hour, 2 background noise conditions of 55 and 60 dB, and then 3 trials of each one of those, so to average. So that's why you're out there all day taking these measurements. And when you just look at mean detection distance, you say, okay, on average, how far away was the car when people pushed the button? Call that like onset of detection. And these numbers like far exceed the minimum spelled out by NHTSA. So the dotted lines on the bottom, which are 6 and 11 meters, correspond to 5 kilometers per hour or 11 kilometers per hour or 20 kilometers per hour of the car traveling. And all these things, even the one with no sound, you're like, oh, that far exceeds what was prescribed. So you're like, well, maybe we can make it way quieter and not have all that detection rate. That's saying people out at 70 meters away are detecting it on average, and that's why we came up with this new measure. So I worked in sonar signal processing for a decade at the Applied Research Lab at Penn State, and so I thought of this as a sonar signal processing detection problem. So like a boat would detect submarines, these people sit there and detect the car. It's the exact same problem. And they're doing it in noise, right? And so I showed these results, which are those mean detection distances. Here's the new one. You get probability of detection on the vertical axis versus distance. So the further away the car is, the lower the probability of detection is. When the cars get in really close, you would think, oh, it's right in front of you. It should be everybody holding the button down, 100% detection. But it never really is. It's like 98, 97. It never quite reaches 100. And that depends on the speed of the car, those 2 curves. The higher curve is the car moving at 20 kilometers an hour. And you can see that it has much more detection further out because of all the tire noise. So above 20, the sound that you're putting out doesn't matter anymore because the tires take over. And then all cars are kind of the same. And on the right picture there is the no sound condition, and you can see how much closer that is. That's just the car by itself. And you can see, probability of detection, even at 0 meters away, never gets to 100%. And at the slower speed, it's only like 0.8. So 20% of people would step out in front of the car. That's not safe. And so, it's just, so even though that had a average detection distance that exceeded the minimum, it's still not safe, in my view. So like I said, there are all these problems with these kind of tests. You're doing them outside. So we were looking at the future. We have a current project from Department of Transportation. It's called the Safety Through Disruption Initiative. And we want to take all these outdoor tests and move them indoors into a virtual environment. There's a picture of my lab. This was at Virginia Tech. I'm rebuilding it with all my lessons learned at Penn State. And what we're going to do is have a virtual acoustic car come by. It does spatially travel, and people will sit and push the button instead indoors. And then we can completely control the environment in terms of background noise, no birds chirping. Or we could do that if you want. If you want like a park-like setting, go to New York, we could measure actual environments and play them back and have people test it. We can do them faster and cheaper. It's like $700,000 to do 24 people. So that's it in a nutshell. I hope that's enough, and I'll take any questions.
This is going to impact everybody's lives, whether you're here or not. I mean, it's just more and more electric cars are going to be out there, and it's something we're going to have to deal with. You were talking about, and before we get to the questions online, there's something I thought about. You were talking about how there are different, you tested out different varieties of sound, basically. Were they all car engine sounds? I mean, what were they, is it just a matter of people have to get adapted to a particular type of sound to recognize as a car?
Yeah, that's a good. There's a huge amount of energy that goes into figuring out what sounds to use. So, if you've ever walked by a Toyota Prius or like the Honda, any of the plug-ins, it has like this like kind of weird like spaceship. To me, I'm like, oh, it's a spaceshipy sound. It's kind of, which is not. They NHTSA early on said no, we're not going to use actual car sounds, like the engine roaring and things like that. And people really disliked it. They thought that their kind of focus group studies said, we don't like that at all. We want something more futuristic, something that points to it being electric. I think it was BMW. I'm pretty sure it was BMW, maybe an Audi. Even hired like Hans Zimmer to come in and help design sounds. And you could do any sound you want, but NHTSA says make sure it's at this level and it has these frequency components in it. On top of that, you can add whatever you want because these are minimums. But yeah, people may have to relearn. If there's 20 of these cars all in a small area in like an intersection, how is that going to affect people's detection of the one that's dangerous? I don't think anybody knows that yet.
One of the questions online, is the frequency or volume more important for pedestrians?
It's both, unfortunately. I wish I could say one or the other. The psychoacoustics, a lot of results from that area. You could go to, there's probably sessions here on it. That it's the thing that seems to be most effective, and we've seen this in our data as well, is sounds that have some sort of modulation. So like an amplitude modulation where it's getting louder and quieter, or a pitch modulation where it goes up and down. That gets people's attention really quickly. But they're also their annoyance factor tends to go up the more you do that. So yeah, it's a balancing act.
This is a question that's kind of obvious, but if you make additive sounds to quiet cars, doesn't that increase the noise pollution in cities?
Absolutely. There's no doubt about it. You just can't beat the physics. Like I said, if you want to use a sound to alert people, then other people are going to hear it. Now, some people are doing research to try to put like an array of transducers on the car and beam the sound just in the direction of where pedestrians would be, and then no one else would hear it. But that's fraught with difficulties because of acoustic propagation. It could make it so that it's super loud somewhere else, and it's hard to predict because the roadway is changing and all the obstacles are changing. That affects how the acoustics propagates.
Seems like something like that in a city would just reflect off buildings and zigzag across the street kind of thing.
That's what it does.
Rick Lovett wants to know, and this is, I think, one of your results, were 20% of the people missing the unmodified car, was it the one with signals?
The really poor one where about 20% were missing it was where it was just the car by itself with no additive sound. So it's the sounds of the tires on the road and sort of the mechanical turning of the car. And that they're just super quiet because there's no internal combustion engine producing the sound at those very slow speeds. This
may be a question you may not be able to answer because it's not really what you looked at, but in comparison, does the probability of detection for combustion engines ever reach 100%?
Yeah, actually. Our first test was General Motors came to us, and they wanted to see exactly that, not in terms of probability of detection, but detection ranges at that time, because we didn't have this measure then. And they did a Cadillac SRX, which is a 6-cylinder gasoline small SUV, and then a Prius, a Volt, and another electric. I can't remember what it was. And yeah, the detection distances of the gas vehicle far exceeded the other vehicles by quite a bit. It was 6 dB louder, higher sound pressure level as you went past the pedestrians, twice as loud.
Sounds like that things are going to change a lot.
Absolutely. Yeah, it's changing day by day. New countries are adding regulations, changing them. I'm part of an SAE, a Society of Automotive Engineers team that has BMW, Mercedes, Honda, Nissan, Toyota, and several other companies, General Motors, that are right now out doing tests and writing up recommendations to governments to modify and try to improve these standards.
Probably the most important thing is look both ways before crossing the street.
If you can. If you're vision impaired, then you have a problem. Yeah.
Thank you so much.
Thank you.
We'll be back for our final presentation in just a moment.